So let's learn to actually calculate a determinant. So this is going to be the cofactor formula done on row I of a matrix. So we're going to say that the determinant of our matrix A is going to be AI1 times the cofactor CI1 plus AI2 times the cofactor I2, and so on until we get to AIN and the cofactor IN. Now I'm absolutely certain that this is extremely useful the way I've phrased it, and so I'll stop. Right? You guys have no idea what I'm talking about, right? Good.
What did you phrase?
This is the cofactor formula.
Oh, okay.
Now, the problem with the cofactor formula is that it's recursive. So, in order to get the cofactors, the cofactor in IJ, so the cofactor is you have your matrix A, but you remove row I and column J. And I mean this in the literal grade school takeaway.
Oh, that's why it looks like that. Okay.
So, what I want you to have from this... Oh, crap. Sorry. I forgot. The cofactor is... Cofactor IJ is plus or minus the determinant of this matrix. Almost done. Categorically, I want this thing to be a number so that doing this multiplication makes sense. You guys with me?
So that Rosie saved you from that, dude.
Yeah, she was right there.
Service dog.
Yep, she would have been right here underneath me, crushed to death. Would have been great. So, if you're looking in your book, this matrix is referred to as MIJ. So it is the matrix A, except you cross out row I, column J. You guys good with this? So this usually needs an example, yes? The plus or minus here, I'm going to replace really quickly with it's -1 raised to the I plus J, which is going to be a thing that you're never going to use. Okay? So it's going to be plus or minus. I'm going to show you where to get the plus or minuses. Good to go? Okay. So let's try this on a matrix. Please note this won't be super interesting on 2x2 matrices, so I'm not going to show it to you.
So 3x3?
Yeah, I'm going to assume you know how to calculate the determinant of a 2x2 matrix. You guys all good with that?
Yes.
So this process, right, I'm going to start with a matrix that's n by n. I'm going to get a giant-ass sum in which I'm going to have to calculate the determinants of a bunch of new matrices. How big are these new matrices?
2x2.
Sadly not. So if I start with an n by n matrix, and then I remove one of the rows and one of the columns.
I thought you were talking about our specific example.
Yeah, so in a 3x3, they'll jump down to 2x2s, right?
Yeah.
We're going to do this multiple times.
Yeah, in a 17 by 17, they're going to jump down to 16 by 16.
And then we'd have to go down.
And then we'll do that one more time, and they'll jump down to 15 by 15 and 14 by 14. And this will, in general, suck
And we go all the way back down.
until we get to 2x2, and then we'll stop. So, this is why the calculator and the computer don't use this method. The number of calculations you have to do is extremely large. It grows with a factorial of the size of the matrix. which is a really, really bad efficiency algorithm. So the computer doesn't do this because it's basically impossible. You do this as a human being because you don't deal with things the same size as the computer. Cool? So I'm going to show you how to do this on 3x3s and 4x4s. I'll probably never ask you to do it to anything bigger than a 5x5 unless it's mostly zeros. That said, pick your row intelligently. If you pick the row intelligently, you can have a lot of zeros, which makes your life easier. That's good. So I'm going to do one first that doesn't have a lot of zeros. Oh, what the hell? I'll give myself a couple zeros. So let's do the determinant on 1, 2, 3, 4, 5, 6, 7, and I'll fill those two with zeros to make my life a little easier. Ah, what the hell? We'll go medium. You guys good with this? So, in doing this, I recommend that you get yourself a pen in a different color and go through and label this matrix in alternating plus and minuses. This is why I don't use the -1 raised to the I plus j. So if I'm going to calculate, I'm just going to take my matrix, I'm going to go through and go plus, minus, plus, minus, plus, minus, plus, minus, plus. Is what's on this? It's just for me to keep the signs straight because I don't want to deal with this shit. So what I'm going to do is I'm going to pick a row to use. Pick a row or a column with some zeros in it. You can do this exact same thing on a column. It works just fine. So I'm going to pick the kind of row with a 0 in it, and I'm going to tend to do these with rows. That's with me? So I'm going to say the determinant of my matrix, call this thing A, is going to be, well, it's going to be 7 times something plus 8 times something plus 0 times something. Okay, see that? That's me just writing down the coefficients from that row. I'm going to have a tendency to take the -1 and put them out front. So after I got my numbers written down, I'm going to go through and say 7's positive, right? 7's got a plus sign on the checkerboard, so that's going to be a plus. 8's got a minus sign, so I'm going to get that minus up front. 0's got a plus sign. You guys with me on that? And then into these, I'm going to put the determinants of my little cofactor matrices, right, my removed guys. I already took care of the plus or minuses. That was the checkerboard. It's on board. So, into the pieces, I'm going to put the matrix where I remove the row and column that my number's in. So, 7's in the first row, last column, first row.
So it'd be 2, 3, 5, 6.
So I'm going to cover those up, and I'm going to get this little matrix here. So I'm going to have 2, 3, 5, 6. Everybody on board? Okay. Then we're going to go to the next one. We're going to remove the row and column that 8 is in. And we're going to get 1, 3, 4, 6. And then save yourself some time and don't figure out what goes in the third one because it's multiplied by 0. You guys see that? If I wasn't going to save myself some time, it would be 1, 2, 4, 5. Right, it would be this little guy because I'd remove the last row, last column. That said, I'm not writing it down because it's zeroed out, so I'm done with it. You guys on board? This is the only way that you're, like, dropping things will, like, as soon as you know they're 0, is going to save you so much time and effort on these. Okay, so now I need the determinant of my two little pieces. So I've got 7 times, and then these ones you know how to do. They're 2 times 6 minus 5 times 3.
12 minus 3, 15. Negative.
Okay, so 12 minus 15. Do things one stage at a time. There's a lot of arithmetic in these. It's really easy to screw it up. Just write down the multiplications. And then we're subtracting 8, and that's 6 minus 12. Okay, so now we can figure out that we've got 7 times negative 3 minus 8 times negative 6. And so we're getting
48 minus 21.
negative 21 plus 48 gives me a grand whopping total of 27. Cool. What is 27? That's the determinant of the matrix? Yeah, and I can think about that as this is going to be the area of the parallel, what's the analog of a parallelogram in 3D? You guys remember? Parallel cube.
Yes.
So it's going to be the image of the unit cube, right? Gets scaled up by a factor of 27. And what's the image of the unit cube going to look like?
It's going to look like a rectangular prism.
No, it's not a rectangular prism because...
It's just prism.
Yeah, it's like a parallelogramal prism, which is sometimes referred to as a parallel pipet.
Oh, that weird one.
You guys remember that?
I do not.
And the scalar triple product would tell you the area of it. You guys remember the scalar triple product?
No.
You have no reason to. So if you haven't had Calc 3, this is not on you. The students who have had Calc 3 should remember parallel pipets and scalar triple products.
I remember they were dumb, and I remember...
No, they're stupid easy. The scalar triple product is where you take the cross product and then the dot product.
Yes, but like...
Good?
Yeah.
Questions on this? You guys think you can make determinants go burr now?
Yes.
How about this? So, you're describing how this would... Oh, wait. Never mind. Figured it out myself.
Can you phrase your question so the video catches it?
Okay, sure. So,
Was it how does this thing turn a cube into a...
now it's how does this thing work in even higher dimensions?
Yes.
Because you're talking about...
Yeah, so they get harder to see, right? So the unit hypercube turns into a thing that has parallel faces, right? Like a bunch of them.
Yeah.
Okay, so there's an analog. It's the area distortion. One way you might think about this is kind of the... well, the areas of these shapes are going to have lots of interpretations depending on what the dimensions themselves mean spatially. Don't think of them in your head as being all spatial dimensions. They can be other physical quantities. Does that make sense? Aaron?